Have you ever seen a weirdo spinning around a beam at a constant angular velocity of 2 radians per second? Or feel what it's like to be inside a washing machine that can spin up to 1000 rotations per minute? Well, personally, I haven't. But in this video, we will teach you the physics that will allow you to do these stunts by yourselves.
What's up? My name is Nicolas Canvisanto from 11.3.
My name is Nielsen Denny from 11.4.
My name is Felix Richard Chan from 11.1, and this is our group's physics project. First of all, let's talk about the objective of this experiment. There are two objectives in total. The first one being to determine the Earth's gravitational acceleration by conducting a centripetal force experiment. And to do so, we have to prove the formulas associated with the centripetal force as well as a bit of Newton's third law.
There are three main theories we need to know before continuing with this video. First off, some basic terms, which are angular displacement, angular velocity, and also linear velocity, and also how they relate to one another. Angular displacement is a measure of how many turns or rotations an object has gone through a fixed point. It can be summed up to this formula. The unit for it are usually degrees or radians.
Angular velocity is the speed of rotation and is measured in radians per second. The formula for angular velocity is angular displacement divided by the amount of time it takes, or
The linear velocity measures how fast an object travels through a linear distance along a circular path. The formula is given by the radius multiplied by the angular velocity, or
Secondly, there is centripetal force, in which, according to Newton's first law of motion, an object with a constant velocity will also have the same magnitude and also direction at all times unless an external force is acting upon it. But when an object is moving in a circular path, for example, a merry-go-round, its linear velocity constantly changes direction, doesn't it?
and change in velocity over time is equal to acceleration, right? In the case of circular motion, the object's inertia causes it to continue moving in a straight line tangent to the circle. However, because the object is moving in a circular path, it must be experiencing an inward force that causes it to continually change direction. This inward force is called the centripetal force.
there are three things to note about centripetal force. It is a force that acts on an object moving on a circular path. Secondly, the force always points into the center of the circular path. And the third one is that the magnitude can be calculated by this formula or this formula, where m is the mass of the object, v is the linear speed of the object, and w is the angular speed, and the r is the radius of the centripetal of the circular path.
For the last theory, there's Newton's third law of motion, which states for every action there is also a opposite reaction.
Moving on, let's take a look at the apparatus needed for the experiment, which are triple beam balance, ruler, stopwatch, loads, string, metal tube, and stopper.
To begin with, we have to measure the mass of stopper and the load using a triple beam balance, as we can see here. Then we place the string inside the tube and attach one end to the load and the other end to the stopper.
Next, familiarize yourself by practicing a few rotations. You can also add points of references at specific intervals on the string for ease of radius measurements. In this case, we added 5 cm for this interval on the string.
Now, spin the stopper 15 times for each of the variation of the weight. The data that we need is the time taken for the 15 rotation to complete. After we get the data, we will divide that time by 15 and we will get the period of rotation.
Please note that in our experiment, the independent variable is the radius of rotation and the dependent variable is the period of rotation, while the mass of the load and stopper are kept the same as control variables.
This means that our data will have 5 variables, namely radius, number of cycles, time, period, and period squared. To find the gravitational acceleration, we need to understand that the tension T1 due to the stopper is equal to the tension T2 due to the mass of the loads. Based on the formula, we are missing three variables: the radius, the period squared, and the gravity. Well, we can calculate by using a scatter plot, where r is plotted on the y-axis and the period squared is plotted on the x-axis. The gradient of the best fit line will give the value of, which in this case is 0.733. And just plug in the numbers to the formula and we will get the gravitational acceleration.
So, T1 is equals to T2. T1 is basically Fc, while T2 is m2 times gravity. Fc is then broken down into m1 times angular velocity squared times radius. We can break down angular velocity into 2 pi per t. So, the equation becomes mass 1 times 4 pi squared per t squared times radius, which is also equals to m2 times gravity.
The percentage error is 5.91% and therefore can be considered fairly accurate results. However, we believe that there are three main reasons that contribute to the slight discrepancies between the experimental and theoretical values.
Number 1. The spinning of the stopper exhibits angles rather than being perfectly flat, or in other words, 0 degrees to the horizontal plane.
Number 2. Since period depends on the time taken for a manual measurement, then there exists an indisputable human limitation. For instance, the experimenter may record the time of 14.5 or 15.8 rotations instead of a perfectly 15 complete rotations.
Number 3. It is almost impossible to precisely spin the stopper at the desired radius constantly at all times. By this, we mean that the radius may slightly increase or decrease during the 15 rotations due to the up and down motion of the string attached to the loads.
So, how can we improve the experiment? The experiment could be optimized or improved with keeping the stopper spinning at a constant angle, as well as a more accurate reading on the number of rotations done by the stopper, and also further the reading of a more accurate radius measurement as well as the markings on the string.
In conclusion, our experiment yielded a value of 9.23 meter per second squared for Earth's gravitational acceleration. Although the percent error is greater than 5%, it is reasonable to conclude that the experiment produces fairly accurate results.